Welcome to the first module of Software Testing Foundations. Now, this module is just an introduction to software testing and what is software testing and how we approach software testing, basically. Now, there are many definitions of testing in general and then testing for software. So, as you know, testing is available everywhere for any kind of systems, like for hardware and for expert system and so on. So, uh, for control system and other things. So, basically, there are many definitions of testing, and then basically the definition of testing getting developed from past to now. Nowadays you have different approach of testing, and then we have kind of changing our view of testing by time. So in 1973, Herzl said that testing is the process of establishing confidence that a program or a system does what it is supposed to. So that was kind of an early definition of software testing, of testing in general, actually. And then during 90s, they said that it is the process of exercising a system because system comes up and then we want to exercise it by manual or automatic means to verify that it is satisfy a specified requirements. So now you have requirements. Now again, during 1996, they said that testing is the process of planning, preparation, and execution to establish the characteristics of a software product. So now we have the software there, and then we have kind of systematic approach like planning, preparation, and execution. So we are getting clear now to kind of systematic view of testing. And then recently, another definition of testing is the process of executing a program with the intent of finding errors. Now, so what is software testing basically? Based on IEEE standard formal definition, testing is an activity performed for evaluating product quality and for improving it by identifying defects and problems. So now and then, software testing consists, uh, during the definition, they said that software testing consists of the dynamic, so we are stressing on these words, dynamic verification of the behavior of a program on a finite set of test cases, suitably selected from the usually infinite execution domain against the expected behavior. Now, come back to this definition. We have four keywords here, which is dynamic, finite, selected, and expected. And basically, our testing definition is, and testing activities actually is located around and swirling around these keywords, like the dynamic execution of the program is important now. So you have to execute the program to test it. Otherwise, it is not a proper testing behavior. So execute a program with specific input values. So you have to execute the program and give input to that program. So that is the first condition of software testing. And then finite. So exhaustive testing is not possible. Testing everything is not possible, and it's also not practical for most real-time or real and complex programs. So testing everything is not possible. For example, imagine that you are testing a calculator software. So you have to test 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, and you have infinity test cases if you want to test everything. So that is what we mean exhaustive testing. So, and then you have selected. So you have many possibilities of test cases. Now, how to select a subset of these possibilities? And then from many possibilities of test cases, how to select those cases which are most likely expose failure in the system. And then finally, we have this expected. So after each execution, we must decide if the observed behavior or observed output is a failure or not. So we have to have some expectation of our test running or test execution. Now there are, from these definition, we have 7 principles of testing. These are basic principles of testing. So the first principle is that testing shows the presence of defects. So now testing can show that the defect is exist and the defect is presented, but cannot prove that there is no more defects. Testing always reduce the number of undiscovered defects, but you cannot say that yes, I tested my software, then there is no bug, there is no fault in my software. As we said, exhaustive testing is impossible. So if it is impossible, instead of exhaustive testing, we have to prioritize, we have to have some selection strategy to select a subset of test cases that are effective of finding errors or finding faults. Now, early testing. In the software development lifecycle, testing activity should start as early as possible. We will come back to this point. You have to start as early as possible to discover the faults, and you don't have to wait until the end of the development process of the software. Defect clustering, a small number of modules may contain most of the defects. So you have to be aware about that. Not all the parts of the software contain faults, and then the faults are not distributed normally distributed around the software. So it is kind of located somewhere in the software. Pesticide paradox. If the same kind of tests are repeated again and again, eventually the same set of test cases will not longer be able. So you have to change your test cases by time, and then each situation need different set of test cases. So the test cases are dependent on the context, which is testing is done differently in different situation. So you have to change the test cases based on the situation you have. And then that is why, for example, when you test for safety critical software, like a control of a train, for example, so that is very dangerous. You have to be careful when you test it, and you have to have some kind of strategy and quality assurance strategy to test, and your testing should be very robust, and it depends on the situation of testing also. So, and also we have the absence of errors fallacy. If the system build is unusable and does not satisfy the user's need and expectation, then finding and fixing defect doesn't help. So you have to test some useful software at the beginning. Otherwise, your testing will be useless, basically. Now, a lot of people are mixing between testing and debugging. There are many things to say here, but basically, we have these points also, but basically, we have that tester and debugger and developer. So tester work is to find errors and to find bugs and to report these bugs. But the developer work and debugger work, basically we are saying developer, not debugger, but we can say debugger also. But the job of the developer during the debugging process is to fix the fault. So the intention here is totally different. As a tester, you are trying to find faults and report it, and your job is not to fix these faults. The job of the developer is to fix these faults throughout the debugging process. Now, you might recognize that I'm saying fault, sometimes I'm saying error, sometimes I'm saying failure, and actually there are many words representing faults or failure or whatever it is in software, and each one of them are used interchangeably, and it depends on the way that you are using it. In the books, in the industrial context, and many other things, in the reports and the academic publications, you are reporting, you are mentioning faults based on the occasion and the situation of the software and the fault appearance. So, for example, we have defects, we have the variance. Sometimes we say fault, sometimes we say failure, and then we have inconsistency and we have error, we have problem, we say problem same time. We say feature, incident, bug, anomaly. Normally we say bug, and that is very common in the industry. Now, failure or fault or defect tend to imply a severe condition, maybe even dangerous condition. That's why most of the time failure is problematic and you have to take care of this. Now, you might use anomaly, incident, and variance, and these words showing that there is some mistake, but they are not as dangerous as failure or fault, but you have to fix them also. And then maybe they show an intended operation rather than a complete failure. So they might not be a failure exactly, but they are anomaly finally, and you have to fix them. And sometimes we say problem, error, or bug, and these are commonly used and generic terms used in the industrial context. So it doesn't matter. In our case, you might find that I'm mentioning bug quite a lot because it's commonly used. So from now we mention bug quite a lot. Now, coming back to this software bug, during the software development process, the first thing you identify is the product specification. And what is the product specification? It's basically an agreement among the software developer and the product owner, or the guy that asking you to produce a software, or the company or whatever it is. And then you have to put the detail, what it is, what it will be, and how it acts, and what it will do, the software, what it will do and what it want to do. So basically we are looking at this product specification, and this will be our masterpiece. So we are developing what the customer wants, and then if you deviate from this product specification, that is basically will cause a bug. So a software bug occur when one or more of the following five rules are true. Your software does not do something that the product specifications say it should do. So your specification says something to have in the software, and then when you hand on the software to the customer, so this software doesn't do that thing. And then second, the software does something that the product specification says it should not do, and that is opposite. And then you have software does something that the product specification doesn't mention, and then the software doesn't do something that the product specification doesn't mention but should do that. And then the software is difficult to understand. Even you deliver the software, but the software is difficult to understand, for example hard to use, and it is slow, or the software says I will be viewed, testing eyes will be viewed by the end user as just plain not right. So you understand that bugs are caused for numerous reasons, but in this sample, of course, in this picture, you can see that most of the bugs are initiated from the wrong specification, or we are focusing on the specification. Maybe the specification wants something, but we are not developing that, or you feel that the software should have something, but then the specification said that that should not have in the software. So it depends on the specification. Now you have the requirement by the customer, and then the classical way of software development is basically the requirement and then design and then specification, design and then implementation and then testing. Now we have four conditions here for representing false. The first condition for the requirement says that everything is going fine, and then if everything is going fine, it means that you are taking the correct requirement, and then the design is specifically meeting this correct requirement, then the design is correct, and then you build based on this correct design a correct implementation, and then the product works as expected. So this is an ideal case of software development. But sometimes you take a correct requirement, and then you design the software based on that in a correct way, but you make a mistake during the building of the software, because you are building on this design, and then during this mistake you propagate this mistake to the product, to the final product, and then you will have a bug. And sometimes you get a correct requirement, and during the design you made a mistake that will not reflect the requirement, and then you propagate this mistake. And then sometimes you take the wrong requirement, and that is the worst case. Then if your requirement is wrong, the whole software will be wrong. So you have these conditions of software. Now you might say that, okay, what is a fault? What is a bug? And how to identify that? You have many situations of bugs. And then during the development of new software features and new applications, you might find faults that are not exist in this taxonomy. But based on the IEEE standard, you have a lot of definition of a lot of situation of faults. For example, you have input output faults, and then input faults. For example, a correct input not accepted, incorrect input accepted. For example, you enter your program must take, for example, a equal to 1 and must not take a equal to b, but when you enter a equal to 1 to the software, so the software shows an error, the software doesn't take it, and that is a fault basically. description of a wrong or mistake, and parameter wrong or mistakes. For example, the output. You enter some input and then the output, the format of the output is wrong, and then that is basically a fault. Or your software will produce a wrong result at the end. You say that 1 plus 1 and the output is 3, then that is wrong, and that is basically a fault in your software. So you have many situations of fault, and this taxonomy is really helpful to identify different kind of faults. For example, you have logical faults. So you are missing some cases. For example, you say if A equal 2, then the output should be 3. And then you are missing some cases sometimes. Then if equal, what if A is not 2? So you have to identify that, and that case is not available in your software, in your developed software. So you are missing some conditions here, some logical faults. And you have computation faults, incorrect algorithm, for example, missing computation, incorrect operands. And you have interface call faults, for example, input output timing. And you have data faults, and these are very important nowadays. For example, incorrect initialization, incorrect storage. uh, you have, for example, incorrect data scope, incorrect type of data, and so on. So all these are problematic situation, and then all of them are identified as false. Now, the cost of bug or faults or defects is varied. So a common understanding of bug cost is that when you discover a fault during early stage of software development, that is the best case. Why? Because you are preventing the fault, preventing the software to be to from a fault that will propagate during the whole software development process. And then if you find a fault during the specification, for example, the cost is nothing, because you change some text or you change some contract, and that's it. But if you transfer this bug to the design, it means like you already spent a lot of time, and that this time is money basically, because you are paying the salary of the software developers and the designer and so on. So when you come back and you find a fault there, it means like you spend more time and you spend more salary on this, and then the whole process will repeat it again. And then if you discover, if for example the same bug during the specification, if you discover it, if not found until the software or coding process, if that fault costed 10 US dollar, at the end it might cost a lot of money, more than 100 US dollar, for example. So it depends on the kind of the fault also. So it is recommended to test or design your test cases during the specification process, and then to evaluate the software from time to time to discover the faults as early as possible. So the question now is, why do we test? Basically, we are testing because we want to prove that our software is meeting some certain level of quality. Now, this means like we are we are having different kind of approach, different kind of objectives of testing. First, we want to find faults, and then we want to get confidence of the system, or maybe we want to measure quality of the system, or you want to show the customer that the software is working fine and we have tested the software, or uh, you want to minimize the occurrence of failure. So there are um, many, many reasons for software testing. So why do we need testing? It depends on the occasion. Basically, we need testing to prove the quality, but also if we don't test, what will happen? In these situations, for example, you might lose some data, which is fine sometimes, which is not fine sometimes if the data is sensitive, for example, or your software will crash. But sometimes for these autonomous cars, for example, you have to test quite a lot, and you have to spend a lot of time on testing because any fault may cause loss of life or loss of a lot of money and loss of a lot of data, and data is money also nowadays, and you have to test, for example, for privacy or for security and so on. So you need software testing anyway. Now, testing terminologies. During this course, we have many things to mention, and we mention all these terms, those terms during the module. But these terms specifically are very important, and we will use them. Now, what is a test case? A test case is a set of conditions or variables that enable the tester to determine whether a system under test satisfies requirement or works correctly. So basically, when I want to test a software for addition, I say 1 plus 1 equals what? I enter 1 plus 1 to the software and monitor the output. So basically 1 plus 1 is a test case. It's just one test case. And I want to test that condition on my software. But a set of test cases, a bunch of test cases, is a test suite, is a collection of test cases that are intended to be used to test a software or a program to show that it has some specific set of behavior. Now, how to run these test cases? You have to execute the test cases basically. Is the test execution the process of running the test cases? And sometimes this running is very costly because you have 1000, 2000 test cases if you go for manual testing. So it means like it will be a time consuming activity. That's why we have test automation. Test automation is the process of embedding the test cases to executable scripts. Sometimes you write a small software to run a set of test cases or to run a test suite which contain a set of test cases. So you just run the test cases, and the test cases will run automatically one by one, and you record the output, and then you deliver the test report at the end. And then you have the test evaluation is the process of evaluating the result of testing and reporting to developer. Now you have white box and black box testing. You will see these things quite a lot, and then sometimes nowadays they say structural testing or logic driven testing for white box. So white box basically is running the test cases on the software while you are having the source code, or you are monitoring the source code, or you are running the test cases on the source code, on the actual code, with the knowledge of inner structure of the system. And sometimes you want to test the software that you don't have the access of the test case of the source code, but you have the software, so you will test the software as a black box. You enter the input and you get the output, and you report the faults based on that. Now, there are many things on testing and quality, and we will come back in detail to this thing. But quality assurance is basically a systematic activity implemented in a quality system so that the quality requirement for a product or service will be fulfilled. So the quality assurance of software is kind of very important. And sometimes we say that software quality assurance is kind of different because you are having the software quality assurance for the software development process, and that is totally different. We don't mention that. We are focusing on the testing of the software as a part of the software quality, or the part of quality assurance. And then this picture is very nice to see that, for example, sometimes you have a set of test cases and you feel like this set of test cases is having a high quality, and that's why you will produce high quality software because uh, you are running a set of high quality test cases. Now the question is, who says that your test cases are having high quality? Who says that your test cases are well designed? So there are many metrics, we will come back to that, to say that to measure the quality of your test cases and to measure the quality of your testing process as a whole. And then that is why it is not guaranteed that a set of high quality test cases will produce a high quality software. It depends for which context of the software you design the test cases also. So when you have a project and you are developing a software, you have different levels of fixing and finding defects. So for example, when during the development process, when you develop and you write the code, you are basically, you know it or not, you are inserting a set of defects because your software will be developed by many developers, and then your writing of the software will not be perfect at the first time, then you will have a lot of defects, of course, and no software without defect, that is for sure. And then when you test the software, you are detecting a set of defects, and then you come back and you fix these defects. And then when you fix the defects and you do some regression testing, we will come back to that. And then it means like you retest the software, and then you will find another set of test case, another set of faults, and then you retest again, and you will retest again and find defects until you need to retest, to release your software. Now you might ask that, okay, only you might think that only the software tester will do the testing, but that is not exactly true because it depends on the size of the company. For example, in the large companies, you have a specific software testing or quality assurance team, but in the smaller and medium-sized companies, maybe the software developer will do the testing. The ideal case is that the software tester should be isolated and separated, and the testing process should be separated from the software development, because you cannot test yourself. When you write a code, it is better to be tested by another guy, not you. But that is the ideal case. And during the development process in medium and small size companies, you will find a lot of people doing the testing. So maybe the project leader will do the test, and then the software developer will do the test, and then you have a tester, and sometimes you release the software to the end user, and you will wait for his feedback as a testing process, as a testing. So it depends, and of course that is the worst case, to do not test your software and to send the software to your customer or to your end user and to ask him to test and report the bugs. Now there are many questions when to start the testing and when to stop the testing process. As we said, starting the testing as early as possible, that is the ideal case. During the software development lifecycle, testing can be started from the requirement gathering phase. And then that is the ideal case. You have to start from that time. In the classical waterfall, we will come back to that. In the classical waterfall model, you have to wait until the whole software will be completed, and that is the worst case scenario. In the incremental model of software development, you have rapid development, and for each iteration, at the end of each iteration, you have testing, which is good also. Testing is done in different forms at every phase of software development lifecycle. It has been done during the requirement gathering phase and reviewing the design phase, for example, or testing performed by a developer or completion for the developer or completion of the code is also categorized as testing. Now, as I said, when you start the testing, when to stop the testing, and that is very serious question. So there are many criteria here, and we say that we mention these things as a stopping criteria for testing. No one can claim that a software is 100% tested, so that's why you cannot stop then, but you have some criteria. So, for example, the worst criteria that I define is the testing deadline. So you say that, okay, I have 2 months for testing or 1 month for testing, and you can spend some time on testing, and then you can say, okay, I finished 1 month of testing and you have to release. But then who says that your quality of the testing is good? So your testing procedure, your testing process should be verified at that time. So that is not a good criteria, but it is a criteria that has been followed by many small size companies nowadays. So another criteria is that you design a set of test cases. You say that, for example, I have 100 test cases, and when I run these test cases and I find bugs, and then I will fix the bugs and run the test cases again, and I'll find another set of bugs, I will fix them and I run again, and then I will not find any bugs, then you can release the software. And then you say that, okay, you have to stop. Also, that is kind of a criteria of stopping. Or sometimes, which is better than these two, the other two criteria, is that the completion of a function and code coverage to a certain level. So sometimes you test the software, but you are monitoring the code coverage. You say that, okay, I covered 80% of the code lines, and then it means like you are visiting the code lines while you are testing the software. And then sometimes you say that the bug rate falls below a certain level. So you test and test and test, and then the bug rate is falling from a high level to some certain level, and then you say that, okay, this is acceptable, you can release. Now sometimes you cannot stop, you need more testing and more testing, and the manager will decide that, okay, this is time to release the software. So it depends on the situation, and depends on the stopping criteria that you define during your development process. And finally, when you test, basically you have a lot of standards, and we have a lot of standards, and these standards are basically defined by IEEE and ISO. And then we have different kind of standards for different testing activities. So, for example, you have IEEE 1008 for unit testing. So when you follow, when you do some unit testing, it means like you are following some, you have to follow some kind of standard. And then you have a lot of other standards. We will post some of these standards, some useful standards for you on Canvas to read and to identify the important parts. So that is for module 1. Um, Thank you for listening. See you during module 2.